Welcome back to Unit 10. Today we're going to be starting our look at probability. We're going to start that by exploring the difference between theoretical and experimental probability. So let's go ahead and take a look at that now. Below us we've got a chart that's laid out with our theoretical versus our experimental probability. We're going to compare and contrast the two, starting with the definition. So the definition of theoretical probability is the number of favorable outcomes that should happen compared to the total outcomes. So we're talking about theoretical, we're looking at something, and this is saying what should happen. However, experimental probability talks about the number of favorable outcomes that does happen to the total outcomes. So theoretical is what should happen in the abstract, and the experimental probability is what actually happens when you go to find that probability. So there are formulas for each of these. When we're talking about theoretical probability, that's the favorable outcomes over the total outcomes. So favorable outcomes would be the thing that we're looking for. So we're talking about flipping a coin and we're looking for heads. Heads are going to be the favorable outcome because that's the thing that we want to have happen. The total number of outcomes in that case would be 2 because there are 2 sides to a coin. And the favorable ones are 1 because we want heads to happen. Our experimental probability formula is the actual outcomes over the total outcomes. So again, experimental probability, you have to actually do the experiment. You had to actually try to get this probability. And the amount that you get, the actual amount, is going to go on top over the total outcomes. So theoretical probability does not change. If it's 1 out of 2, it's always going to be 1 out of 2. However, experimental probability may be changed each time an experiment is conducted. So remember that when you're doing the experiment, you're going to be changing the amount of times that you either get a favorable outcome or an unfavorable outcome, and that's going to change the probability. So now let's take a look at that in practice, going with example A. So here at example A, it says Jamie spins a spinner pictured 40 times. So our spinner is up there in our upper right-hand corner, and it says the arrow lands on the section labeled blue 18 times. So that's important information that we should know. It's landed on blue 18 times. Compare the theoretical and experimental probabilities of the spinner landing on blue. Write the probabilities as fractions in simplest form. So taking a look at our theoretical probability of landing on blue, we can see that there's only one section of blue in our spinner, and there are 4 sections totaled. So in theory, we should get 1 blue every 4 times that we spin it. So our favorable outcomes is on the top, and our total number of outcomes is on the bottom. Since there are 4 spaces on the spinner, and each of them is equal, we have 4 chances, and because we're looking for blue, that's our favorable outcome, that's going to be on top. Now we need to take a look at our experimental probability. And our experimental probability is what actually happened. So, since we actually got 18 times that we spun the spinner out of 40, that is our experimental probability. But now we need to make sure that it's in simplest form. Because both the numbers are even, I can divide them both by 2. So 18 divided by 2 is going to give me 9. 40 divided by 2 is going to give me 20. And my simplest form is 9/20. So let's compare our 2 probabilities. So if I'm going to look at the theoretical probability and turn it into a comparison, rather than comparing with fractions, I'm going to turn them into decimals. So 1/4 is going to be 0.25. Now if I do 9/20 as a decimal, I'm going to get 0.45. So we can see the experimental probability and the theoretical probability are not the same. In this case, the experimental probability turned out to be much greater. But the experimental probability could also turn out to be worse or the same. It depends. But the theoretical probability will never change. It's always going to be 1 out of 4. So that brings us to the question at the bottom that says, suppose Jamie spins this spinner 1 more time. What is the probability of landing on the blue section? And we can say the probability is still 1/4. The new spin is not affected by previous spins. So no matter what the experimental probability is, whatever we're going to do next continues to be the theoretical probability because it does not change. So even if you are flipping a coin 100 times in a row and you get heads 100 times in a row, the theoretical probability of getting tails on the next spin or in the next flip is still 1 out of 2. The theoretical probability does not change and it is not affected by previous experiments. Now let's take a look at example B. Here we are at example B, and it says the table shows the results of 60 rolls on a fair number cube. So that's important information. We're going to be talking about 60 rolls of a fair number cube labeled 1 to 6. Compare the experimental and theoretical probabilities of the following events and write the probability as fractions in simplest form. So we're going to talk about the theoretical probability of landing on 5 and the experimental probability of landing on 5. So our theoretical probability of landing on 5, if we're taking a look at a fair number cube labeled 1 to 6, there's only one 5, and that is out of 6 sides of our number cube. So that's our theoretical probability, 1 out of 6. Now we need to take a look at our experimental probability, and it says that it rolled 9 times out of 60. So again, we have to reduce that to simplest form. So we're going to divide both the top and the bottom by 3. 9 divided by 3 is 3. 60 divided by 3 is 20, so that's going to be 3/20 as our simplest form. So we can see that our probabilities are not the same. Now we're going to talk about the theoretical probability of landing on a prime number. So the first thing we need to do is identify the prime numbers on our chart. So our prime numbers are going to be positive numbers that have 2 divisors. So 2 and 1, 2 is going to be a prime number, 3 is going to be a prime number, and 5 is going to be a prime number. 1 is not a prime number because it does not have 2 different divisors to multiply to give it that number. 1 only has 1 divisor. So our prime numbers are going to be 2, 3, and 5. So our theoretical probability of rolling a 2, 3, or 5 is going to be 3 out of 6, or when I reduce that to simplest form, is going to be 1/2. So now I need to figure out how many times it experimentally landed there. So I have to add 12, 14, and 9 because that's the total outcomes that happened. 12 for the 2, 14 for the 3, and 9 for the 5. When I do that, I'm going to end up getting 35. So there's going to be 35 out of 60 possible rolls that I got a prime number. So now I need to reduce that to simplest form. And since they end in 5 or 0, I can divide them both by 5. 35 divided by 5 is 7, and 60 divided by 5 is 12. So that is my experimental probability. And I can see that 7's a little bit more than half. So the experimental probability was greater than the theoretical probability. But if I were to roll the number cube again, I would still have half a chance of getting a number that is prime. Remember, theoretical probability does not change. Experimental probability changes every time that we do an experiment. That brings us to the end of this video. So if you like this video, go ahead and throw us a thumbs up. If you love this video, go ahead and throw us a sub, and we will catch you in the next one.